I recently read that scientists have generated electricity from rain and that this method could produce up to 100 watts per square meter. That'd be only a factor of 4 or so less than solar panels. I've seen headlines saying that it could one day overhaul our power grid. Big if true. Let's have a look. Many thanks to all our supporters, especially our patrons in Tier 4 and higher. This channel would not be possible without your help. If you enjoy my videos, please consider supporting me on Patreon or joining this channel right here on YouTube. Now about how to make electricity from rain. This research comes from a group at the National University of Singapore. They generate electricity by letting water flow through tiny plastic tubes. That's surprising because to generate electricity you need to move charges. And normally the water at the wall of the tube will build up polarization, alright, but the charges would just stick there. So no moving charges, no electricity. In the new experiment now, the scientists solved this problem by looking at the flow of water interrupted by air, like you might have in rainfall. Because that doesn't allow the charges to get stuck, they need to move along with the water drops as they trickle down through the tube. And from that, one can create electricity. It's really clever and basically a way to convert gravitational energy into electric energy. In their experiments, they used a tube of approximately 30 centimeters in length and 2 millimeters in diameter, like a straw really, and fed it with a mix of water and air at 80 milliliters per minute. This generated a power of 0.4 milliwatt. According to the press release, they used 4 of these tubes to power 12 small LEDs, so that's a clear demonstration that it indeed works. They calculate that the conversion from gravitational potential energy to electricity has 10% efficiency. How do they get their estimate of 100 watts per square meter? You just have to ask how many of these tubes you could fit next to each other vertically. They're about 2 millimeters in diameter, and leaving aside details of the packing, you can estimate that roughly 250,000 will fit into a square meter. Multiply with a 0.4 milliwatt per tube, and you get roughly 100 watts per square meter. Yes. But first, it's worth mentioning that the LEDs which they talk about are these little indicator lights that you can find on a circuit board, not your normal household LEDs for room lighting, which need a few watts. But much more important is the question of how much rain would you need for those 100 watts per square meter. They don't calculate this in the paper, but I did. That'd be 250,000 tubes per square meter, so 250,000 times those 80 milliliters per minute that they used. That's about 20,000 liter per square meter per minute. Rainfall is typically quoted in millimeters per hour, and heavy rain is something like a centimeter per hour. The rain you'd need for the 100 watts per square meter, in contrast, is something like a kilometer per hour. If it ever rained that much on your roof, you'd have bigger worries than your electricity bill. Another way to look at it is that if you collected rain per square meter and channeled it into those tubes, you could only run a few of those per square meter. So I think at best you generate a few milliwatts per square meter with this idea. We could, and indeed I think we should, ask, what's the point? Why not just collect the rainwater and run a turbine with it? This indeed exists for, say, rain pipes, and if you have a big roof and heavy rain, that can produce a few hundred watts. The efficiency of these turbines is usually in the range of 50 to 80% or so much higher than what those people propose. So this idea definitely is not going to overhaul the power grid. But that isn't to say that the idea is useless. The benefit of this idea is that you don't need a turbine. You need no moving parts and no collector. This could be useful, for example, if you have a situation with a lot of water condensation going on, maybe in a factory. You could generate electricity from that trickling water. It's also more easily portable, I'd imagine, so you could maybe use it for some measurement devices or such. In summary, it's a really clever idea, and there's good evidence that it indeed works. But I'm afraid it's not going to revolutionize energy production. So keep on dusting the solar panels. What is consciousness? This, I believe, is currently the biggest open question in science, and it's getting more relevant by the day as artificial intelligence approaches consciousness. However, a big controversy has erupted around one of the most popular theories for consciousness, integrated information theory. It's been accused as untestable pseudoscience, and yet it was recently tested against a competing theory. Let's have a look. Integrated information theory, thought up by neuroscientist Giulio Tononi, says that consciousness comes from the number of connections between different parts of a system, quantified in one big number, phi. More phi, more consciousness. But even simple systems like electronic circuits can have phi, so pretty much everything is a little bit conscious. It's therefore a panpsychic theory. Tononi also holds a patent for using IIT for a consciousness meter, basically, and GeekWire claims that IIT proponent Christopher Koch is part of a startup called Intrinsic Powers that wants to put this to work in clinical practice. I don't know about you, but I find this slightly worrisome. Imagine the nurse scans your head, and even though you're talking to her, she finds you're not conscious. Then what? The problem with IIT is that in practice one can't calculate phi even for the brain of a worm, because for that you'd have to calculate the connections between different parts in all possible partitions. It's a computationally extremely difficult problem, so you have to simplify it, and that makes the theory ambiguous. That the media has nevertheless portrayed AIT as a leading scientific theory prompted a group of more than 100 researchers to write an open letter in 2023 in which they expressed their concerns. They wrote that, given its panpsychist commitments until the theory as a whole is empirically testable, we feel that the pseudoscience label should indeed apply. My kettle is deeply offended. Just in March, another commentary appeared in a Nature Neuroscience paper whose authors write again that IIT is indeed unscientific because its core claims are untestable even in principle, and we appreciate that the word pseudoscience should not be used lightly, but there are good reasons to think that it applies in this case. A group of IIT enthusiasts responded claiming that the theory is objective and testable, and that attempts to label as pseudoscientific a theory distinguished by decades of conceptual, mathematical, and empirical developments expose a crisis in the dominant computational functionalist paradigm. In other words, stop calling our baby ugly. Let me be honest, I find most of the criticism of IIT to be off the mark. We frequently use theories whose core assumptions, the axioms, are strictly speaking untestable. Think of general relativity, which rests on the axiom that space-time is a differentiable four-dimensional Riemannian manifold. No one ever tests that. We test consequences that we derive from the axioms, and that you don't like panpsychism isn't a justification to discard the theory. It's not how science works. Who knows, maybe carrots are conscious, they're just very introverted. And in any case, some researchers recently managed to squeeze predictions out of IIT and one of the competing theories, global neural workspace theory. According to this theory, you become conscious of something if parts of the brain, most importantly the prefrontal cortex, broadcast a signal across the rest of the brain. The prediction from IIT was that a conscious person should show steady and complex activity in the back of the brain because then phi is large. Workspace theory, on the other hand, says that there should be quick bursts up front in the prefrontal cortex whenever something raises to consciousness. The researchers used a variety of brain measures like fMRI and magnetic field readings, and also signals from electrodes that some of the 256 participants had implanted for medical reasons. They monitored the participants while they were looking at images. Both theories got some things right and some things wrong. The strongest signals linked to conscious perception were found in the back of the brain, supporting IIT's claim that this is where conscious experiences are generated. However, IIT also predicted that these signals would be unusually complex and tightly connected, and that was not observed. Workspace theory, on the other hand, predicted that becoming aware of something would cause a brief burst of activity in the front of the brain, but that burst was mostly absent. Still, it did correctly predict that more areas of the brain become involved during conscious perception than during unconscious processing. What does this mean? Well, one thing it means is that the root of consciousness is actually in signal processing from sensory input, because that happens in the back of the brain as opposed to executive function that happens in the front of the brain. I think the real story here is that consciousness research is making progress at all. It's becoming a real science. Personally, I think it's idiotic to believe that consciousness can be quantified in a single number. But if that turns out to be correct, I say we print it on cheese labels. Now 30% more aware. Did we misunderstand the double-slit experiment, the most famous experiment in quantum physics? We usually interpret it as proof that light is both a particle and a wave, the essence of quantum physics. Yet in a new paper, a group of physicists disagree. It can all be explained by particles, they say. And this paper appeared in PRL, which is basically the top journal in the field. So let's have a look. For the double-slit experiment, one directs laser light at a plate with two microscopic slits. That's the double slit. On a screen behind the slits, one then sees an interference pattern, that is, bright and dark regions. This is a typical wave phenomenon that you can also see in water waves or sound waves. Light from both slits adds on top of each other, and where crest goes on top of trough, the light cancels out, so that's a dark spot. Where crest meets crest or trough meets trough, they add up, and that's a bright spot. Why does one need laser light? Is it just that physicists really like lasers? They do, but one actually does need the laser light because you need the phases of the light, that is the places where there are crests and troughs, to all be the same. Otherwise, they add up and cancel in random places and you don't see the pattern. But now we can reduce the intensity of the laser light until there are only single quanta of light, individual photons traveling towards the slits. And the odd thing is now that the photons, which are particles, build up an interference pattern one by one. This seems to show that a single photon also behaves like a wave. It must go through both slits and interfere with itself. That light behaves both as a particle and a wave is often called complementarity. So far, so good. Not that it makes sense, but we've gotten used to it not making sense. The authors of the new paper now say we've got it all wrong. Light is all particles. It's just that there are both light photon states and dark photon states. The dark photons can't be detected, and that's why there are some light and some dark spots on the screen. The dark spots are where the dark photons go. One of the authors told New Scientist, according to our explanation, we just need the particle aspect of light. The new thing about their treatment is that they don't just calculate the probability of a photon arriving at a particular place. In their calculation, they include a simple model for a detector, like an atom, that can absorb a photon and calculate the probability of this detector detecting something. In the normal treatment, one doesn't do that. They then take the state of the quanta in the light apart into those that will make a detector light up, that are the light photons, and those that won't. Those are the dark photons. The relevant point is that these dark photons are not just vacuum. They're part of the quantum state of the laser light. By the way, this video comes with a quiz that lets you check how much you remember. That said, while their treatment is genuinely a new way of looking at the double-slit experiment and the maths looks fine to me, I don't think the interpretation makes sense. For one thing, both the light and dark states of photons still go through both slits. So I think it's misleading that the authors say it's all about particles. The other thing is that, like in the normal treatment of the double-slit experiment, the energy of the light that goes to the dark regions is zero. Again, that supports the interpretation that those dark states aren't anything like particles. However, that doesn't mean the idea is useless, because that treatment with the light and dark photon states, odd as that sounds, is mathematically more general than the usual treatment in which one relies on this wave interference. There are cases where the usual interference approach wouldn't work, but their approach would, and the authors propose several experiments to study this. They also say that understanding the distinction of light and dark states can improve the storage and transmission of information, because you don't want to dump information into the dark states where you can't receive it. Honestly, when I read the headline, I thought this is bullshit. But having read the paper, I think it's a matter of framing. This is a genuinely interesting new way to think about an old experiment. But I don't think that talking about dark states of light is going to make quantum physics any less confusing. One of the leading quantum computing companies, D-Wave, has been accused of fraud. They aren't even the first quantum computing company to face such accusations, and they probably won't be the last. Let's have a look. The recent accusations against D-Wave come from Kerrisdale Capital, a short-selling firm. Their report doesn't hold back. They write that the current stock valuation of the company is ridiculous for a company that has no clear path to profitability and sees stagnating customer growth, as its approach is increasingly recognized as a commercial dead end. D-Wave is riding quantum hype, but with a core technology that cannot stay afloat. Ouch. But just exactly what do they think the problem is with D-Wave? Kerrisdale argues that D-Wave's quantum annealing can't and won't do anything a conventional computer can't also do. Quantum annealing is basically a specialized form of quantum computing that's designed to solve optimization problems. Rather than performing general-purpose calculations like gate-based quantum computers, annealers are optimized to find the lowest energy state of a system. This is great for specific problems in principle. In practice, it's unclear whether it isn't easier to just use a conventional computer. The accusation of fraud is based on D-Wave's murky use of hybrid calculations that combine quantum with non-quantum procedures. Kerrisdale says it's unclear what, if anything, the quantum part is even good for. They say they interviewed a former D-Wave engineer and asked them what is the added benefit of including quantum in a hybrid solution, to which the engineer replied, "I'd say the added benefit is we call it quantum, and this is a benefit to some in the marketing department." Another former employee said that there is no proof that any optimization problem is solved faster using D-Wave's quantum systems. The report also criticizes D-Wave's claim that they were first to demonstrate quantum supremacy on a useful real-world problem, according to a press release from March. They said they had outperformed one of the world's most powerful classical supercomputers in solving complex magnetic materials simulation problems with relevance to materials discovery, and that they completed in mere minutes what would have taken a conventional supercomputer nearly 1 million years. This is a simulation of the Ising model, the same model that IBM already used in 2023 to claim quantum utility. The simplest versions of the Ising model are analytically solvable, and these more complicated ones have been simulated extremely efficiently on conventional computers. Indeed, it didn't take long after the IBM quantum utility announcement that another group said they'd beaten IBM's quantum result with a conventional computer. Many experts believe that D-Wave supremacy claim will soon suffer the same fate. And even if that wasn't so, these obscure Ising model problems have hardly any real-world relevance unless you are a theoretical physicist working on the Ising model. So I think Kerrisdale has a point. They quote an anonymous executive at a large multinational technology company and former professor of quantum physics who sums it up with, D-Wave is selling bullshit. That said, one has to enjoy this report with some caution. As I said, Kerrisdale is a short-selling firm. That is, they are investors who make money when a company's stock price falls. That doesn't mean what they say is wrong, but it means they have a motivation to see D-Wave's stock fall. It isn't the first time that a quantum computing firm has been accused of fraud. 2 years ago, another publicly traded quantum computing company, IonQ, was accused of deceiving investors over the maturity or existence of their quantum devices. They have been more careful with their press releases since. In January, the short-selling firm Capybara Research claimed that Quantum Computing Inc. deliberately deceives investors. The report claims, among other things, that the company lied about its relation with NASA. Instead of having 2 NASA contracts and 4 subcontracts, they have, according to NASA themselves, 1 contract valued at merely $26,000. The report also claims that the company has repeatedly signed fake deals just to put out press releases, presumably to the end of pumping their stocks, and that they claim to have opened a foundry when they just leased a small space for an R&D lab. And Rigetti Computing, yet another quantum computing company, recently faced allegations of misleading business practices. Several law firms launched investigations into whether they exaggerated their technological capabilities and market readiness. Maybe the real quantum breakthrough is making investors' money disappear in 2 places at once. Thanks for watching. See you tomorrow.